Want to do a couple of basic work problems here. So example number one, since work is force times displacement, let's go ahead and write that up there. Work is force times displacement. Assuming, of course, that force is constant, then if I have a 3 Newton force pushing on a box and it goes 4 meters in the direction in which I'm pushing, then it's just a straight up multiplying 3 newtons times 4 meters, and I get 12 Newton meters. And in the context of energy and work, Newton meter is a joule. So 12 joules of work. If I'm pushing opposite the direction of movement, so the box is going this way, so that's the direction of the velocity, but I'm trying to stop it, I'm going to slow it down, I'm taking energy out of this. In other words, I'm applying negative work, I'm slowing it down, and so the work in this case, in terms of if I make to the right positive, then this becomes positive 4 times negative 3, or negative 12 joules. If I make to the left positive, then the work I'm doing is positive 3 newtons times negative 4 meters, and I still get negative 12 joules. So the direction that I choose for the positive direction does not matter ultimately. Or from polar form, they are 180 degrees apart. So if I draw my two vectors, 4 meters and 3 newtons, the angle between them is 180 degrees. And so it's the magnitude of one times the magnitude of the other times the cosine of the angle between them. And I would also get negative 12 joules because that's equal to negative 1. And then if I use in terms of I hat, making I hat to the right, positive I hat to the right, I get negative 3 newtons I hat times 4 meters I hat. And when in rectangular form, you multiply the common components. In other words, you multiply the I components together, so that's the 4 meters and the negative 3 newtons, and I get negative 12 joules again. Example number 3, I now have the force being applied at an angle, 37 degrees from the vertical. Now typically the angle is given from the horizontal, but for some reason in this example I decided to do it from the vertical. And so I need to break it into components. I need to figure out how much of that force is to the right if I am doing the rectangular form right here. So when I break it up, that's the 37 degree angle down here. So this would be the hypotenuse times the sine of 37 degrees, hypotenuse times the cosine of 37 degrees. And so if I establish I hat and j hat like that, it's 1.8 newtons I hat minus 2.4 newtons j hat because it is downwards. And I end up with multiplying the parts that are parallel, so I'm going to be multiplying the I components together. There's no j component for displacement, so this piece of the force does absolutely no work at all. And so 1.8 times 4 is 7.2. Now if I did it instead from polar form, that is 3 newtons down at that 37 degree angle, so that's 37 degrees. But I care about this angle right here, so it's the complement, so that's 53 degrees. So my 3 newtons at a negative 53 degree angle, because that's fourth quadrant, times 4 meters times 0 degrees, because that is straight to the right. And it's the magnitude of one times the magnitude of the other times the cosine of the angle between them, similar to what we did on the other page. And whether it's positive 53 degrees or negative 53 degrees is irrelevant because it's the same cosine value. And we end up with 7.22 joules. Or if I just simplify it down to how much of that force is in the direction of movement, it's 1.8 newtons times 4 meters, and I get 7.2 joules. The difference here is a rounding because when I did this, I assumed that the sine of 37 degrees was 0.6 and the cosine was 0.8, and really 37 degrees, it's a little bit off of that. That is the rounded angle for a 3-4-5 triangle. From straight up polar form right here, so we don't have the picture anymore, but I've given a magnitude and direction for two of them, and so work, magnitude of one times magnitude of the other times the cosine of the angle between them. And again, doesn't matter from which one you subtract from which. So 241 degrees minus 130 degrees, or flip it around, the cosine value is the same, and we get a negative value, which means that ultimately the force is hindering the movement. And then in rectangular form, go ahead and make it three-dimensional. Not really going to draw that one. At least this one up here I can draw, but this one I can't really draw. And you multiply the parallel components. So I multiply those together, I multiply those together, I multiply those together. Now I could multiply that times that. So if I did that, I'd have 4 newtons I hat dot 2 meters j hat, which would be 8 Newton meters I hat dot j hat. That, since those are perpendicular to each other, that is equal to 0. So that part really doesn't matter. And so any of the cross components, the I dot j, I dot k, j dot I, j dot k, and so on, the only ones that will survive are the ones where it's I dot I, j dot j, and k dot k, because I hat dot I hat is equal to 1. And ultimately, we end up with 10 joules. -4 plus 6 plus 8. And now we have the last one. This is a calculus-based version. So if the force is 3x squared I hat, and I'm going from 4 meters I hat to 9 meters I hat, I'm integrating. This is from the formula. Work is equal to the integral of f dot dx. And there's another video where I step into this relationship right here. But if you haven't seen calculus, or this is 151, you don't need to worry about this one, but this is just how you would deal with it if we're dealing with a force that is not constant. And so we're basically doing an antiderivative or an integral, and we end up with x cubed from 4 to 9. Plug the 9 in, that's 9 cubed. Plug the 4 in, that's 4 cubed, subtract, and you end up with 665 joules.